Well, good morning, everybody. Thank you for being here today to listen to me talk about our electrification journey at Harbour Air. My name is Erika Holtz. I am the lead engineer and project manager for the eBeaver program at Harbour Air. Our contribution is most about the end user. We're not an OEM, we're an airline with an R&D department. So I would like to run this that if you have questions, please raise your hands as we go rather than do it all at the end, because I'm most interested in telling you what you are most interested in hearing about. So I'll tell you a little bit about who Harbour Air is for those who don't know and why we're doing this, how we got here, a bit of the technical details if you're interested in that, how we got to first flight. Oops. That went too far. How we got to first flight. And I think the key for a lot of us is the lessons we've learned and what we want to share with other people who are in this sector. And then I'll get into what's next and our future goals. So Harbour Air is one of the largest seaplane operators in the Americas. We fly over 400,000 passengers per year to 12 different destinations. We have 45 aircraft. They are all seaplanes. We have mostly a fleet of Beaver aircraft, single otters, some twin otters, and a couple of caravans. And we are one of the first airlines in the world to try flying an E-plane. One of the reasons that Harbour Air was interested in pursuing this is because of this route map. Harbour Air flies mostly 30-minute average flights. So we don't have very long missions and we don't climb to super high altitudes. Most of our flights are under 1,000 feet. If you're looking at this route map, for example, Seychelles to Nanaimo, that's a 15-minute flight. And it's usually done at about 500 feet max. So our energy requirement is actually really quite low. Also, because we have all of this infrastructure and we already have the aircraft, it's a lot easier to get to electrification by converting an existing aircraft that's proven rather than a clean sheet aircraft for this particular application. So when they talk about advanced air mobility, we like to say that, well, we've been doing that for 40 years. A little bit about our journey to date. So it was back in May of 2019, our founder, Greg McDougall, announced when he was inducted into the Canadian Aviation Hall of Fame that he was going to electrify his entire fleet. To be honest, I think everybody at that dinner laughed at him. In May of 2019, there was not a lot of adoption of the idea of electrification, which I think was probably a bit of a fire under the team. You know, when we were told we were going to electrify the aircraft, I'm not sure that we believed that it was capable, but having other people tell you that you can't do something is very motivating. So since 2019, this is a bit of a timeline. We'll get into more details. But in January, we met magniX. And they were an engine company looking for an airframer. And we were an airline looking for an electric engine. Nobody else was particularly interested. I know magniX had been looking at many other companies. They'd gone to Viking. They'd gone to Kenmore. They tried a variety of places. Nobody was ready to make that step. And our founder, obviously from May of that year, Greg McDougall, was very much looking for anybody who was willing to try and sell him an electric engine to put on his aircraft. From about March of 2019 till December 10th, that's the time frame we had to design, build the aircraft in order to fly it within the time frame dictated by the marketing teams. So we flew first on December 10th, 2019. Then, of course, there's the 2020 year. So not much happened during that year. October of 2021, we were able to announce we got some funding from the BC government to help keep the program going. And the following year, we completed our first point-to-point flight by flying from the YVR, the Richmond International Airport, to the Victoria International Airport. That's one of the things I think that Harbour Air brought to the table that's different from some of the work that's being done out there is we have the ability to test the aircraft in our operational environment. So then adding on to that, we tried doing multiple flights. So we flew from YVR to Salt Spring Island and then from Salt Spring Island to Victoria. I'll talk more about the lessons learned there. And last year, we've applied for our design approval organization. I think in the States, you guys call that an ODA. So we're going for our DAO so that we can certify many of the components ourselves. Baseline aircraft. It's the Beaver. It's been around a long time. Many people looked at us and said, why are you converting such an old airframe? And a part of that is because it is an old airframe. It's a known aircraft. You can strap moose to the floats and the aircraft doesn't care. It really doesn't matter what you do to this thing. So we wanted to take an airframe that everybody trusted to behave exactly as predicted, and then only convert what we needed to convert to make it fully electric. So there's very little external to the aircraft that changed. This is a 5,600-pound single-pilot, 6-passenger aircraft. We took the entire firewall forward off, stripped out all the belly tanks and anything to do with the engine instrumentation, and replaced it with the following. First, the engine. So 450 horsepower Wasp Junior radial 985. It's a good engine. We didn't want to change how much power was going to be available for the aircraft because that could change some of the actual behaviors and characteristics. So we installed these components, which includes the Magni 500 motor, which we derated down to 338 kilowatts, sorry. And that equals 450 horsepower, so we would have the same amount of power available. There were some interesting things with this build, mostly because magniX was very new to aerospace, and they really wanted to design, they're like, we're going to compete with the PT6. So what's wrong with the PT6? Well, it's kind of heavy, so we're going to make this as absolutely light as possible. So it was very, very, very light, but it didn't drive any of the accessories off the engine, which made the aircraft integration actually really quite complex and heavy. We had 2 different oil systems in this thing with cooling pumps running off the low voltage system. So it was dictated that for the inverters in the motor, there would be liquid cooling, and they wanted it to be a dielectric oil. They were concerned about using standard oil, so we had a silicon oil system specifically for the motor and the inverters, but we have a standard Woodward governor that had to run off turbine oil. So we had 3 pumps in this thing with 2 different oil systems. So it was quite heavy and a little bit difficult for our poor AME over here to manage. And it's a very standard then system. You see at the bottom there, there's a standard ducted over heat exchanger. That's where the oil ran through to cool everything. What else we have on here? The cockpit cabin. I'd say that one of the things we really wanted to do is try to limit the changes in the cockpit for the pilot. Pilots don't like change. They really don't. So we wanted to make sure it was as easy for them as possible. So we had to replace some of the controls and interface. A little bit more about that in a minute. This is the electric engine we installed. I know we call it a motor. The regulators have dictated if you're going to actually try and certify an electric motor as an aircraft engine, you have to call it an engine to be able to Part 33 certify it. So it is an aircraft engine. It's an electric engine. This particular one is 336 kilowatts. At 1900 RPM. That's important later for some of the noise characteristics. Question. All right, so the question is the difference between energy density and power density. Is that correct? So energy density is how much energy you can actually pack into your battery module, right, per kilogram, right? So it's always rated as your watt hours per kilogram. And that is definitely one of the areas that we struggle with. Nobody pretends right now that the energy density of lithium-ion batteries are high. It's an area that needs to be improved. One of the things for our application, though, is it really doesn't take very much for us to go from being a 2-seat aircraft to a 6-seat aircraft in terms of the energy density. For example, the aircraft we're working on right now, we have cells that have about 220 watt hours per kilogram energy density, and we're predicting we'll be able to put 2 to 3 passengers in. We raised that up to 350 watt hours per kilogram, which are some batteries that are on the market, coming into the market right now, and we are now a 5 to 6 seat aircraft. It doesn't take that much for it to get that much better. Right? And you were talking about the CFG? Yeah. So our batteries, so there's some definitions that are still being worked on with the regulators to define what is a battery cell, what is a battery module, what is a string, what is a stack. It's quite complicated. So for our architecture, we had 3 strings of batteries. So we were running at 537 volts was our highest voltage. So each string had to add up to 537 volts. So in this particular arrangement, we had 8 modules in series and then bussed together 3 different strings, right? Then physically, they had to be stacked in a variety of ways to ensure we kept maintain the CFG, because that was very critical to us to maintain the CFG, but also to not spread the weight out too much, because you will end up with moment of inertia issues, right, with the aircraft. Exactly. You don't want to distribute the weight. You don't want to carry all the weight out at the, your wings or in your tail or way too up front. We wanted to centralize the weight as much as possible. For this arrangement, actually, I'll talk a little bit more about what happened with the batteries, but the prediction in the beginning, we were actually going to have 9 modules per string, and we were going to have a couple modules on the firewall. We had modules in the fuel bay, and then we had a stack of modules in the cabin. The fit form of these batteries was actually quite awkward. If you looked into the fuel bay, we have this pretty large fuel bay, but we could only put 2 modules in there, and there was a whole bunch of empty space because you couldn't stack any more modules in there. So I think it was, originally, I think Greg McDougall's vision when we started it in February was the aircraft we were building was going to be the certification version of the aircraft. It didn't take us very long. I think we were a couple of months in. We're like, we cannot stack this thing in any kind of arrangement that's going to allow for passengers, even if we had the weight. We sort of gave up on that ideal, told him we're going to have to do that in the next iteration, and stuck most of the batteries just in the cabin behind the pilots and just decided, okay, this is just for proof of concept, stick most of the batteries in the cabins. Yes, they were stacked together to maintain C of G in this 3-string arrangement to get us to the 537 volts. But we did bus these 3 strings together, and that's one of the things that is in my lessons learned a little bit about this one is when you bus the 3 strings together, at the time, possibly due to some of the instrumentation we had, there was no way to know if you lost a string because you still see the same voltage on the outlet. It'd be like 3 fuel tanks feeding into one feeder and you're only reading at the feeder line. If one of your fuel tanks became blocked, you wouldn't necessarily know because you still read half a tank of fuel. So we're still reading that we have fuel in the battery, but it's no longer flowing into the engine. And that was so. In our next iteration, we decided we would go away from a bus system to a single string per inverter. So we moved to a 4-string system where 1 string of batteries could feed 1 inverter. But of course, the complication with that one is you lose a battery string, now you lose power, right? So we're still playing with what the best idea is from a system safety analysis and from a use case, is which of those is better. The bus system is actually better for having a DC to DC converter to knock down power to the low voltage system. So there are some improvements there. Plus, if you lose a string, you don't lose any power. But there's the possibility of cascading failures then, right? So failure with one inverter could cascade to the other inverters because of the bus system. So the single lane seems better in that respect. But then, of course, if you don't have the reliability in your battery system, like in your battery management units, then your risk of loss of power becomes higher. So these are still things that we are struggling to identify which is the best architecture, which is why we have our experimental aircraft that we're flying to change these architectures. We try this architecture, see what we think about that one, have our system safety guy do some analysis, and then switch to a different system and see if it works better from a physically working perspective, and then also from the system safety analysis. There's a whole mix in the batteries. So within the modules, there's series and parallel, and then you've got the strings in series with like the modules in series, and then the strings in parallel. So it's multiple. It is an AC motor. So the inverters do convert from DC to AC. Don't ask me too much about that part. I should have clarified, I'm a design approval representative, a delegated engineer in structures. My job was to install all these black magic boxes onto the aircraft and show that it worked at the aircraft level. Within the components, I am not that familiar or knowledgeable. So how the motor works, he could probably explain a little bit better, but it's not really. That's a magniX question. We'll get them to join us next year. You're welcome. Thank you for your question. So I think we went through a bunch of this, the battery modules, the strings, their battery management units. So I think one thing that's key on this slide, though, is understanding that every single cell in every single module is monitored and reported to the pilot for voltage and temperatures. I think that's really important from a system safety perspective to understand just how much data is actually being collected and reported by the system. So the battery management unit is very important. It's monitoring, communicating temperatures, currents, voltages. It manages delivery of the power. So it's both got the communications in it as well as the power distribution. So the battery management unit sends all the power to the engine, or to the inverter, portion of the engine, but it also does all the monitoring, reporting over CAN to the HMI display to make sure the pilot has all the information. There was also an intention, this is one of our interesting lessons learned, DC to DC converters are very noisy from an EMI perspective. Our first flight, the pilot could actually not communicate over the radio, we discovered after first flight, and that was because the DC to DC converter in the BMU actually wiped out the radios. We did do an EMI test with magniX. I'm not quite sure how we missed this particular item. I think we didn't have any of the radios maybe far enough away. We weren't testing it. We didn't test it quite deep enough. So we ended up having to disconnect the DC to DC converter and add 2 more batteries of these shipset batteries into the aircraft architecture to ensure that we had enough capacity in the low voltage system to run our flights. Circling back to those cooling pumps, not only were they noisy and took up a lot of space, they also are like, 27 amp, 25 amp. So their draw on the low voltage system was huge. We ended up installing 4 of the, was it EarthX or TrueBlue? The the EarthX batteries. We had to install 4 of them on the aircraft because we didn't have the DC to DC converter anymore. So we weren't feeding low voltage, like charging the batteries during flights. So we had to have 4 of them just to have a 45-minute capacity in the system to ensure we had some reserve. So that was an interesting lesson learned. So we don't currently have a DC to DC converter installed in our flying machine. We've installed all the new strings, now the non-bust system. We now have to figure out how to bust that power back together to feed the DC to DC converter. But that's what we're going to test on the aircraft next. Our team back home is working on that right now, trying to figure out what the electric circuit is going to look like in order to install, I think we're using a crane DC to DC converter to try and then take some of these batteries and get some weight back, because our new iteration might allow for an actual flight test engineer. So I might actually get to fly in our aircraft for the first time if they can figure out how to put this DC to DC converter in. One important fact, also the lockout tagout switches. So these were installed for maintenance safety, right? So that you can cut the voltage in half. I referred to the fact that we wanted the cockpit layout to remain as similar as possible to not disrupt pilots. So for anybody familiar with the Beaver, this is relatively similar. You see the standard 6-pack, although we do have a Garmin G5 in there. There are more switches, of course, in order to turn on the system. It's a little bit more complicated, but the feedback to the pilot is relatively similar. The display up in the middle, that's the engine instrumentation. We do have an extra display over to the right. That's more for experimental R&D purposes. The intention was to leave this as similar as possible so that the pilot change from a piston Beaver to an electric Beaver is not a significant amount of training. And if you talk to our pilots, we have one of them here this week, they pretty much say it flies like a Beaver. There's nothing that exciting. Everybody comes up, hey, tell me about flying the electric Beaver. They're like, it flies like a Beaver. There's nothing really interesting to report other than it's a little bit of a faster Beaver. So this was during 2019 when we were doing our ground testing. It was really one really interesting opportunity that we have as a float plane installation is we can do our ground runs on the ground attached to our beaching gear, and we can run full mission profiles. So we were actually able to simulate all the different missions that we wanted to fly with this aircraft on the ground without having to invest in an expensive simulator. That's just another picture of the same thing. And then, of course, the which? You can't see my mouse. You're talking about in the cabin there? Yeah, so that shows the batteries, yes, inside the aircraft of iteration 1. I don't think I forgot to mention this. So this was one of our other complications when we were building this thing is we had estimates of all the weights. So it was really interesting with magniX being in Australia, EP Systems being in Utah, and us in Vancouver, trying to coordinate this installation without actually having any parts. So we had to estimate where we were going to put everything in the aircraft. We had step files in CAD. We had a guy who sat there all the time and stuck these boxes into the airplane and said, okay, this is approximately where they're going to go. The dimensions of the components were relatively correct, but every component that was delivered by any supplier in the entire chain came in 10% heavier than they had told us across the board. And so one of the things we did that we actually get to say, yay, look, engineers, we did something smart for once. When we were installing all the components on the firewall, we did not weld anything to the engine mount. We had the engine mount built, and then we used clamps. So all of the structure, when it arrived, our AME could adjust the location in the engine mount to adjust the weight and balance to ensure we stayed within the CG envelope, which became actually very important because we ended up having to use that ability because everything came in 10% heavier. The one fit that also didn't work out properly, which we also had an adapter plate for, was when the magniX motor, I don't think it had arrived yet. This was still in the design phase, but we had already sent our engine mount out for fabrication. When we got a red flag, we woke up in the morning with a note from Australia that said that the step file they'd sent us was, I think, 30 millimeters out in terms of the diameter between the attach points for the engine. And they were highly concerned we were going to have to remake our engine mounts. But we had again, one area we've accounted for something that we knew would possibly be a problem because we didn't have any components in hand. We had a welded piece onto the engine mount, but then we had an adapter plate and we didn't pre-drill the holes. So we were able to drill the holes on assembly and accommodate the fact that this had an incorrect dimension in it. That was just a filler. So the other interesting thing that was going on this year is because the components were not proven to any actual environmental standard at the time. We had significant limitations on the operations of them in terms of weather. So none of the components were allowed to get wet. And I don't know if any of you have been to Vancouver. It rained on. So in Vancouver, we are known as Raincouver. And this was November, which is really our rainy season. And so in order to get through the testing, because as I said, we had a very short time frame to do this, most of our components arrived in September and October, and our marketing team had decided to tell the press, we're flying December 10th. We told them repeatedly, I can't guarantee that. A, I'm not sure the engineering work is going to be done. B, the weather likely won't cooperate. They said, no, you got to be done by this date. So we cleared out the hangar. Actually, fortuitously, we use this hangar every year for a Christmas party. So it always gets dumped at the beginning, like the end of November, and the ground gets painted. So they dumped the hangar, and we stuck the nose in, and we ran all of our high power testing with the nose inside, the tail outside, and ran all our simulations and failure modes. And there's our finished build. What am I doing on time? Not too bad. So first flight considerations. In Canada, the experimental process is a bit different, especially if you aren't an OEM. And so we weren't sure how we were going to get to the point where Transport Canada would actually give us a flight permit for this thing. So in April of 2019, I called my Transport Canada handler and said, this is what we're going to do. And after he told me we were crazy, he said he would call a meeting. And so at the end of April, we had our very first meeting. I wouldn't call it an ITB meeting. It was not quite there. But they called in and they organized anybody at Transport Canada who thought that they should be involved in this conversation. So we had a phone call with 21 of the Transport Canada specialists and sat on the phone, I think, for about 3 hours. And they told us all the things they thought could possibly go wrong with this thing. So we made a list of every concern that they had. And once a month, we would meet and we would tell them how we had addressed their concern. And by the time we got to about September, our list was cleared, which was really good, except for one item that kept coming up. And that was submersion. Transport Canada was incredibly concerned about what happens if you ditch this aircraft in the water, right? And although we know we talk to various experts, if you take a battery module and you put it in water, they're like, well, we do that all the time to ensure we don't trigger thermal runaway. It's how you cool it down. I'm like, okay, well, what happens if it enters in? Well, it'll likely short circuit. Okay, well, what happens outside the module then? I don't know. That was the primary response across the board. Nobody really knew what would happen if you took an energized system from all the way from the engine back to the batteries. If it was running and the energy was flowing and you submerged this thing fully in the water, what would happen? Nobody had a good answer for that one. And I tried pitching the idea to my CEO of testing it. He was not very interested in submerging a $1.5 million asset just to see what would happen. So what we ended up doing instead was putting in mitigations in place to ensure the safety of the pilots, right? This is where, in order to get to flight, basically it became, okay, we're just going to limit what you can actually do and make sure that you've protected the pilots and the public. So we had things like, okay, we're only going to be allowed to take off and land on the water. We can't fly over land at all, actually. And if you've been to Vancouver, you can take off the river and head out to the ocean, and then you can turn around and come and land back. But that also means you can't be flying in very high winds because you need to be able to probably land or take off with a bit of a tailwind. So we were limited to 10-knot winds. And we agreed to whatever they wanted just so we could be able to fly. So no rain, no sand, no fog, no smoke, like pretty much any environmental item you could possibly think of. We were so, nope, lightning. Okay, you got to be 25 nautical miles away from any lightning activity. And then for submersion, it was like, okay, well, if we limit you, so you're always over the water. Well, okay, you're not going to hurt anybody except the pilot. So now how do we save the pilot? So we ended up wrapping the entire battery bank in a cell block blanket that weighed 30 pounds. But these cell block blankets, have you seen them on airplanes? They have the small pouches. So if your phone goes into thermal runaway, you throw it in the pouch. It contains the heat, the fire, and the toxic gas from the thermal runaway events inside this pouch. So the cell block blanket actually contains most of the events, the ejecta that comes out of a thermal runaway event. So we covered the entire battery bank in this cell block blanket. But that wasn't good enough because one of the more interesting things, and I know poor Mike here had to bring this silly thing up, we called it Auto, as autopilot from Airplane. The BMU had originally started out about yay big and 20 pounds. It ended up being this tall, barely made it into the aircraft, and sat right next to the pilots. And so the BMU collected, as I said earlier, all of the energy from the battery. So you had, your 600 volts sitting right next to the pilot. So we had to go researching, and we found this really cool saran wrap looking stuff. That's that one's a noisy one. Current proof, right? You wrap this around the BMU and it'll actually contain electricity, right? The voltage won't break through. So we had to then wrap that and the batteries in this saran wrap and go back to Transport Canada and say, look, if he ditches on the water, we've contained the thermal runaway inside the cell block blanket. We've contained the electricity behind this thin film saran wrap. It will likely penetrate it eventually because water will find its way in, but now we have enough time. The pilot, if he's not out in 2 minutes, he's not getting out, right? So we bought the pilot time and they accepted that as our mitigation for submersion. To this day, we still don't have a spectacular answer for what happens with submersion. So we started a project with the National Research Council of Canada, and we're doing a hazardous operations study to examine exactly what happens. And we're going to use some of our old battery modules that we still have, because we've had to do a replacement, to do some actual testing of larger style systems and possibly with an inverter, at least in there, to get more representative of an entire system. The other item we installed that was really important was the emergency off switch. This was actually, if you went through our functional hazard assessment and mitigation, almost every single one said, shut it off and land. So, okay, the engine's doing something you don't want, shut it off. The battery's doing something you don't want, shut it off, right? It's a Beaver, it can glide, it'll be great. So with all those limitations and mitigations in place, Transport Canada on December 7th, they actually, it's one of the few times I've seen them do this, they walked to our door, they came up to us and physically delivered the flight permit to us on the Friday so that we could fly on the Monday. Yes, but they haven't tested to a particular standard. Right? That's the problem, is there aren't any standards that say, okay, this is the process by testing you should do, and this is the data that you need, and here's the pass-fail criteria. That doesn't exist. So that's one of the things we're working with the NRC on, is we want to, at the end of the hazardous operations study, we want to end up in a place where we have a standard that could be used in both aviation and maybe electric vehicles as well. That's just basically, this is how you test for submersion of a high voltage vehicle system. That's one of our deliverables we're hoping for. So after that flight and skipping through 2020, we've performed to date actually 89 flights, exploring takeoff, cruise, range, climb, noise, cooling, balk landing, loss of power, and of course, operations. How does this thing operate in our environment? It's a very boring slide, but it's the most exciting slide to me. This is why this became a commercially viable vehicle. So when we flew our first flight in 2019, it was an 8-minute flight. And because of everything coming in 10% heavier, one of those things was the battery modules. So we ended up having to remove a module from each string. So we went from estimating a 15-minute flight down to an 8-minute flight. None of us thought this was going to be commercially viable at that time. It was proof of concept. We could show that we could fly an electric vehicle. Beyond that, it wasn't going anywhere. But as we started testing the aircraft, we realized something very interesting, and that was the cruise performance was significantly improved. We knew takeoff was better. Wow. That was cool. So we knew takeoff and climb performance was improved, but the most critically important one for commercialization was the power for level flight. So we reduced the power required from 62% of max power down to 41% of max power. It was significant and not expected by anybody. I think we had estimated maybe a 10 to 15% improvement in efficiency, mostly because of the propeller. The Beaver still has very old technology propeller on there. So the new tech propeller was estimated 10-15%. We didn't know how much more improvement we would get, though, from the reduction in drag, reduction in the cooling drag in particular. I mean, if you think of the radial as blocking most of the thrust from the propeller. So this, though, not only did it mean we were more efficient in cruise, but when you calculate your reserve, it's based on your cruise settings. So instead of needing 66% of the battery pack dedicated to reserve, we only needed 35% of the battery pack dedicated to reserve, which cleared up the rest of it for flight. So we actually got to a 33-minute flight with that particular battery pack. We've changed our battery pack recently. We just flew 11 flights on the new battery pack, and we're up to, I think, 34 minutes was our longest flight to date. We might be able to get a smidge more out of it. 62% of 450 horsepower is what's required in the Beaver to maintain level flight, and it still drags its butt through the air. If you've ever watched it, it's very nose up attitude. Sorry, there was a note in there. 62% of max power, 450 horse, was required to keep this thing in the air, especially at 5,600 pounds. And if you did it on a hot day or at any higher altitude, it was worse. For us, 41%, and it does not matter whether it's hot out or if we're at a higher altitude, although we're limited to 3,500 feet, it's 41%. So that was significant. And anybody who's flown a Beaver knows it's not enthusiastic about taking off and climbing at 5,600 pounds. We did some on-the-ground testing, company testing. It was not calibrated tools. We were able to determine we're close to 300 pounds more thrust with this aircraft. So even though we have the same horsepower, the 450 horse, because we derated the engine, due to the efficiency in the system and the improved propeller and drag resistance, we're getting about 300 pounds more thrust out of it. So the climb performance is actually vastly improved for the Beaver. And the third most thing that was critical, especially for those of us in an urban environment, is the noise reduction. So the OEM Beaver with the R985, it spins at about 2,300 RPM for takeoff. We reduced that down to 1,900 RPM, so we're spinning slower. We also changed from a 3-blade prop to a 4-blade prop, so the blades were actually a bit shorter, so the tip speed significantly reduced. And so again, this was not validation testing, but it was company testing. Across the board, we reduced noise by about 20%. Or sorry, 20 decibels. This was one of the most interesting things, though, was the operational point-to-point flights, actually seeing how this thing would behave if we took it from one of our bases to another. Did I skip ahead? Testing under our actual operating conditions, like taking it down to our dock, dispatching it from the dock, teaching the dock hands how it's different, flying it to another location, and then charging it. I think I just put some eye candy in here so I could talk over it. One of the interesting things, of course, was charging. I think I'll get into that in the lessons learned. I just wanted to show this. Can I make this go? Mostly we show this so people know that we aren't just computer CGI. This is a real flight. And it's got Mount Baker in the background, so most people can recognize the skyline. Every time we flew the aircraft from one point to another, we had to chase it with our company 180. That was so we had the mechanics with us, but B, we were carrying our charging equipment as well, because none of the locations that we fly to had appropriate charging. So yeah, bring your own charger. Every dock we went to did not have even 220 volt service available. So we called ahead to Salt Spring, we called ahead to Victoria. We had to pay an electrician to come in and at least wire in the 220 volt 40 amp service so we could plug into something. So we flew our 7 kilowatt charger along with us each time in the 180 and charged on location, but it changed what was a 3-hour charge process into a 16-hour charging process. So charging infrastructure is going to be critical for us to be able to operate this in our environments. Other things we learned that were very interesting was nonlinear charge rates. So we might be able to get up to 80% very quickly, but the last 20% could take a lot longer. I think most people know that. Charging protocol standardization. So as we talk to more and more people, like we are talking with H55 in Switzerland, we've dealt with a variety of people. So we use, in North America, we like to use a charging protocol called CCS1. Europe likes to use CCS2. Tesla's using NACS. There are about 4 other different protocols out there, and everybody's using something different. So it is going to be something we're either going to have to try to come up with a common standard. I know there's some companies out there trying to do that. Otherwise, we're going to have a lot of adapters. The other thing was additive heat. Something you don't think about is when you're fueling your aircraft, you're not heating up your engine. If you're charging your batteries, you're heating them up. So they heat up during charge and discharge. We had some interesting things with this too, is for a variety of reasons, but when you take off, this particular system, I would say, had some undersized components in it. The fuses in particular and the batteries were undersized. And so when we went to take off, if we weren't above a certain state of charge, then we would exceed the current limits on our battery fuses. So we were not allowed under this first system to take off with less than 70% state of charge. And so that's something I think when people are designing electric aircraft is to take into consideration, what is your working load, but what are also some of your more outliers? And it's not even a failure condition, right? This isn't, oh, I evaluated failure conditions and these are okay. This is a version of a working load, but finding out what your worst case working load is. And so when you're dealing with some of these, I think they're learning more now, but the suppliers that we were dealing with at the time, not working in aviation, we're used to defining, okay, well, you're going to be using 220 Great. So we're going to give you a 240 amp fuse. Well, what if we take off at 50% state of charge? Now we're at 350 amps and your fuse is going to blow. And they'd already decided, well, but that's your working load. They don't understand how it would work in particular because of the different power requirements at the different states of charge. It also means that there's an interesting condition. If you get to the end of your flight and you want to do a go around, you have to pay attention to what your state of charge is and how much power you can push then, because you might have components that aren't sized for that. Because if you're down at a low state of charge, you've already flown your half-hour flight, you're dipping into your reserve, your state of charge is relatively low. You're probably going to be at 20 to 30% voltage, which means your current's going to be quite a bit higher when you try to push full power. So I know that you guys might have heard of the pipistrel. They actually have in their operations manual, it derates the power after you get past a certain state of charge. For commercial passenger aircraft, we're not entirely sure the regulators are going to accept that. We might have to define the zero fuel point, the point at which you can no longer push full power because your system can't handle the increased currents, right? One thing that was really interesting that we learned in particular because we were taking it to our operational environment is how the environment influenced the temperatures in the batteries, but not just the overall temperature of the batteries, but the differential of the temperatures depending on where the battery was in the aircraft. So we're a float plane, we're sitting on the water, the ocean is cold, it's an incredible heat sink. That meant the batteries that were in the belly were much more affected by the heat sink. And so they rapidly cooled faster than the rest of the batteries. And the battery bank inside the cabin actually stayed quite a bit hotter, A, because they were all together, and B, they were wrapped in this silly cell block blanket. So that didn't help. But I think one of the keys for us was making it clear that, especially if you're looking at a retrofit where you have different zones of where you might put the batteries, those zones might be at very different temperatures because the environment is very influential over these batteries. Because we don't carry liquid cooling on board, they are passive air cooled only. If you have battery modules up in your forward of your firewall, you're likely going to have a whole lot more air cooling on that due to airflow through the cowling than you are anything that's in the cabin. And then anything that's in the fuel bay or out in the wings might also have more conductive cooling than those inside. And the problem with differentials is it's not too bad during flight. You can get a differential to give you a warning. But if you're charging, if you exceed a 15-degree temperature differential, most systems will shut down and stop charging on you because it's not good for the system for the voltages to be too disparate, for the temperatures to be too disparate. So there's a lot of influence from the environment that I don't know that the OEMs are necessarily taking into consideration because most people aren't trying to operate and charge it in the operational environment yet. State of charge, state of health, cycle life, this is all something that is, they're still trying to figure this out. When you buy a cell, they're going to tell you that on a deep cycle, 0, 100 to 100 and back down to 0 is a cycle. You can get 1,000 cycles out of a battery. But how you use it is really going to influence what your true cycle life is going to be. If we are operating this between 40 and 80%, we're in the happy zone for the batteries. That's where they prefer to be. They don't like to be much lower than 40%. They don't actually really like being up in the top 20% either. How fast you charge it, what temperature you're charging it at, all these things are very much going to influence the life. So it's the operator who's really going to dictate the cycles of that by how they use it. So we know for Harbour Air, because we're likely to use this thing in particular in the beginning as a tour machine, we'll stay between the 40 and 80% likely because we'll do very short 15, 20-minute tours. But they're going to want to fast charge this thing, like rapidly charge it every single time. And we have to be cognizant that can decrease the cycle life. So one of the things we're working on is a ground conditioning system because the temperature that you charge it at is going to influence the cycle life. So our intention is you bring the aircraft into the dock, plug in the charger, but also plug in a ground conditioning system that'll flood the batteries with a liquid medium and sense the temperature of all the battery cells in the entire system and moderate the temperatures to ensure we are at the optimum temperature of the batteries. This will also be really important is because of the additive heat issue. When you charge and discharge, you keep heating up overall. We need to be able to bring the temperature back down so that every time we dispatch the aircraft, it's between 15 and 20 degrees Celsius so that we can get multiple flights out of a day. So we're designing this year right now is the ground conditioning system because it's going to be a bit of a challenge to figure out how do you flood the system, control the temperature in all the different zones to bring them all down, bring them all to the same temperature and the temperature that you want it to be, and then evacuate the system in the same time frame as charging it. And since we're installing 150 kilowatt chargers at our locations, our anticipation is we're only going to have about half an hour to charge these things. So can we flood the system, moderate the temperatures, and evacuate the system in the same time frame? Yes. So the modules we're using right now have liquid cooling provisions. They've got a port in and a port out. I do not have an image of what that looks like inside. Is it a plate inside? So there's a plate inside, floods in, floods the plate, and then comes out the other port. One thing I would say that's sort of interesting with our supplier, I'm not sure why they designed it this way, the ports are on the top. So it's going to come in, flood, and then come out. So evacuation might be interesting. And how do we know that it's fully evacuated? Are we going to put the aircraft on a scale and flood it to see how much weight went in and then evacuate it to see how much came out? Are we going to do some sort of measurement? What's the tolerance that we're going to be allowed? Because if we leave anything in there, we've just eaten into our payload, right? So it's very complicated to figure that out, but we think it's critical to be able to have any kind of life out of these things, right? To be able to use these for as long as possible, we need to take care of the batteries, which means we're going to have to figure out how to ground condition them. We've talked to Beta about buying their cube system. We're not using it right now. If you go to Wentz on the Lake, you could see the charger we're using. If you go to Wentz on the Lake, they have fabulous food there, by the way. They're fantastic. Our charger is sitting in a crate over there. It's a 75 kilowatt ABB charger. It is a car charger. And I know if you talk to many people, experts in the industry, everybody agrees we probably shouldn't use car chargers, but that's really all we have access to at the moment, aside from, yes, Beta's come out with their charging cube. It's actually reasonably priced. We just haven't come to an agreement on purchasing any of those, because the other issue we have, again, is the power source. Right? They still need 400 and 100 amp service, and we don't have that at any of our dock locations. So we're talking to BC Hydro, right? To the provider of our energy to find out what are they willing to do. But the way BC Hydro works is you pay them to install a substation. They don't, and then you pay them for the service that you get afterwards. It's quite lovely. It's really quite fair. We're like, okay, we'll pay to install some equipment, and then we'll pay to use it, and then you can also sell it to other people. It's a great system. So we haven't quite to come to agreements there for those things. But yes, the Beta Cube is really quite cool. We like that one. It's nice and compact and mobile, especially that they have a 40 kilowatt version and an 80 kilowatt version that would be more mobile than some of the larger solutions. Yeah. Yeah. The other issue is as soon as you get above 750 volts, you can no longer use a 220 volt single phase power source. You at least have to be 220 volt three phase or 480 volt higher. And they don't build any chargers that can actually run off 220 volts single phase service that'll get you up to 800 volts. The limit right now is 750. And we know this because we were trying to source chargers to bring our aircraft here, right? We didn't want to ship our charger with us. We wanted to use something local, and we were unable to do so because there's no 480 volt service available at the Seaplane base. They could bring us 220 volt single phase, but we couldn't find a charger that could run off that could get us all the way up to 800 volts. It could only get us to 750, which means we'd be taking off, I think we estimated like only 75% state of charge, which is not enough energy for us to do a flight over the airfield here. So yes. Yeah, so he's wondering if we're in a very low temperature, how long does it take to bring the batteries up to our operating temperature? We actually haven't tested that this much. We refer to our baby as the princess. She spends most of her time in a hangar, and I don't know if she's been below 10 degrees Celsius, but it is pretty quick. Once you turn the system on and push a bit of power, the batteries heat up really quite quickly because they don't have any liquid cooling in them right now. If you're sitting on the ground, there's no ram air, there's no airflow at all, they heat up relatively quickly. Our intention would be that if you were dispatching the aircraft again, you'd have this ground conditioner system hooked up, and it would be keeping the batteries at the temperature you want them to be. I would also use this ground conditioner if you're storing the aircraft. Say you don't want to use the aircraft for 3 months and you want to store it. You would store it attached to a ground conditioning system so that you can keep all the modules and all the cells at the optimum temperature for storage, which I believe is something more like 0 degrees Celsius, right? So you'd want to keep it quite cold to, again, elongate the life of the batteries. These are still numbers that we're going to be, making sure of, because I know Tesla changed their minds recently. And when you take your Tesla, you're supposed to program it, telling it you're going to a charger. It starts heating up the batteries before you get to the charger because it now wants you to charge at something like 50 or 60 degrees Celsius. I'm not quite sure why they've decided that this is the best way. I don't know if it means that it accepts the charge faster, so it makes the charging faster itself, which is really, the public really seems very keen on making sure they can charge as fast as possible, but that doesn't mean you're taking care of the batteries in terms of state of health. right? So it's going to be a bit of a balancing act to try and manage, because it is not a huge cycle life. 1,000 cycles of the deep cycle is not huge. It's another area that we're hoping that they can improve in the near future. I think I already talked about loss of string when strings are bussed together. And loss of a string when strings are not bussed together leads to a loss of power. So that is something I think I mentioned earlier. Balancing was also a big issue with our first battery pack. These are things that I think, again, talking to the OEMs of the batteries, making sure they understand that they deliver all the information to the operator that the operator needs to know. There were things that these batteries were doing that we didn't know they were doing it, and it destroyed the battery life. And with this particular one was we had a bit of a parasitic draw in one of the strings, and we couldn't find where it was. So what we were doing instead was we were balancing the system. So we would turn on the lockout tagout so the system would all balance, which was fine. That worked okay, but we wanted to be able to monitor it since we were leaving it on all the time. So we hooked it up to the laptop data system and monitored it through the software provided by the OEM. So we could tell because that also checked all the temperatures and voltages and information on the cells. So we could ensure we weren't heating up anything too badly. Unfortunately, what they didn't tell us was when you had that system hooked up to the aircraft, it physically engaged every cell balancer on every single cell every 15 minutes. So basically, if we left the aircraft on overnight or for a week or a month, every 15 minutes, every cell balancer went on and worked the cell just a little bit. But that meant every cell was working just a little bit every 15 minutes of every hour of every day of every week of every month for about a year, until the system said, you know what, I'm not happy anymore. You've depleted us too much. It really ruined the battery pack. And that was simply, we didn't know that there was this piece of software, that this is what the software did. And they didn't know that we should know this. So I think that was one of an important lesson learned dealing with these suppliers who are creating these batteries, is they are not operators. They're not pilots. They don't fly these aircraft. They don't understand how the operator is going to use it. And therefore, they're not necessarily giving you all the information that you need in order to operate it, not necessarily safely. They're very concerned about making sure everything's safe, but all the other things that you could do to the system that they don't know that you would use it in that way. This is sort of a random lessons learned. Commonality of markings, placards, cable colors. We're not there yet. If you look around the world with EASA, ANAC, the FAA Transport Canada, everybody's doing something slightly different. As an example, orange is typically used for flight testing, right? Everything that's orange is usually flight testing. But the electric vehicles have been using orange cables for high voltage. And so we really need to come together and make some decisions as to what are we going to mark things, how are we going to color code them to make it as obvious to the AMEs and the pilots as possible. We're not aligned in many areas if you're going towards certification. So DO-160's environmental testing, it doesn't have anything in it about high voltage, it's all low voltage. DO-311 versus DO-311, that has to do with thermal runaway testing. Most of that specification was written because of the Dreamliner single battery fire that happened. It's not intended for propulsion system batteries. So there's a lot of work that needs to happen there. I could go on. There are lots of specifications. And actually, if you I have a colleague speaking on Friday, and he's talking a lot about the certification aspects and challenges that we're facing in that side. Things to consider: your takeoff and landing weight will be identical. You're not going to be able to take any advantage of your fuel burn. So as we scale this technology up to larger aircraft that actually require using fuel burn in order to reduce their landing weight, they're no longer going to be able to do that. So it could have some structural implications. They're also heavier when they're on the ground. Is your ground infrastructure designed for that? For us in particular at Harbour Air, that means we're leaving beavers tied to the dock at almost full gross. Not the best idea. If you have a lot of wave action, you could sink the aircraft relatively quickly. Emergency response. So again, coming back to some of that markings and placards, there are some interesting things out there like automobile rescue charts out of ISO 17840. This is something where you can have a quick reference card that fire departments have. And it's basically a layout of a car. I don't think they have very many of them for aircraft, but if there's a fire and fire department is being dispatched, they have these quick reference cards. They could flip to it and say, okay, this is the Electric Beaver. Here are where the high voltage lines are. Here's where they have the batteries. Here's a port for flooding the system if we have to try and cool it to reduce the chances of thermal runaway. Here's some information about how to extract the pilot. We're not using that in aviation, and so it's something that we've brought up a few times to say, I think we need to improve this side for safety for the fire departments and emergency personnel to ensure that A, they can rescue anybody inside the aircraft, and B, they don't hurt themselves doing so. So we are keeping our experimental aircraft flying. There are a few reasons for that. We have opportunities to simulate flight conditions so that we can inform our engine and battery suppliers about the things that we're learning so they can make changes. One of the interesting architecture things that batteries are dealing with right now is some of them are looking at thermal runaway containment, but they don't stop cell-to-cell propagation. But what that means at the aircraft level is now I have an incredibly hefty venting system because they're not stopping thermal runaway. So you could have a module with 1,000 cells in it, and every single cell is going to light off, and they cascade in an order. So that could take, depending on the size of the module, 10 minutes, 20 minutes to cycle through all those cells. And you've got to deal with then 900 to 1,000 degrees Celsius and some ejecta, chlorine gas, other things coming out through your venting system that you have to vent overboard. There are other ones that are designing with a cell-to-cell propagation mitigation inside the module. So that means if one cell goes into thermal runaway, it won't cascade to another one. That makes the modules much more heavy, but it changes the venting system that I have to install because now I might only have to deal with, 100 degrees Celsius for 6 minutes. So we can test some of those things at the aircraft level, integrate them, and then feed back that information to our suppliers. So we're going to continue to fly our experimental aircraft while we build the certification version with lessons learned from that aircraft. So with that aircraft right now, what we're also looking at doing is working on determining some certification basis and means of compliance things. So some things that Transport Canada has raised to us is they're like, okay, you've changed the propulsion. We're like, yeah, so that shouldn't affect most of your flight characteristics. They're like, well, how do you know? Well, because it shouldn't affect your flight characteristics. Yeah, but how do you know? Okay, fine. So we're going to take the aircraft and actually fly to the edges of the envelope with our flight test pilot so that we can do that with the baseline aircraft. So he'll go up in a 5,600-pound piston Beaver, fly to the edges of the envelope, provide his subjective analysis of the flight characteristics, and then he'll repeat that testing in our development vehicle and tell us whether there's a material difference in any of the flight characteristics. So we can feed that back to Transport Canada and say, it's negligible. We didn't change lateral stability, right? We didn't change any of these particular items. We changed performance, and we're happy to do performance testing. A big step for us over the next year, Jen, is with that ground conditioning system, being able to prove that we can do multiple flights in a day. If I can't prove to my ownership that they can fly it 8 times in a day, they're not going to want the aircraft. And I've talked a lot about the different architectures we're trying out. We need to revisit some of those planned architectures based on what we're learning off this aircraft. And so our expected performance of the aircraft, we anticipate a 60-minute mission that includes the reserve. So we're hoping people will negotiate with their regulators to define what their reserve for their operation should be. And that'll tell you then how much time you have for your actual mission. The first issuance of the STC with the battery technology we have right now, we expect 2 to 3 passengers, but we do know there's 350 watt hours per kilogram cells being put into the market right now. With those ones, we can get up to 4 to 6 passengers. So we will have a second STC program that runs immediately following that will add in these new batteries so that we can, because once we have the certification path and we know how to get there, it should be, I'll go with, relatively easy to swap the battery pack. As I said, design requirements for little changes as possible. Our current flying machine does not have reversing capability, but our operation has mandated that we shall include reversing capability. Charging interface, we're still trying to decide what needs to be in the aircraft versus what can we put outside. So commercialization steps, this is where we go next. You may have seen there was news recently that we signed a letter of intent with magniX to purchase 50 engines. It secures our supply chain for the Harbour Air fleet, also allowing us to do third-party conversions. Harbour Air doesn't just want to do this for themselves. They want to convert other people's aircraft and provide electric aircraft to anybody who's interested in having one. We'll continue working with our battery suppliers to optimize the final configuration. We are targeting 2026, kind of end of 2026 for our first STC. That's not our commercial version. As I said, that'll be Harbour Air's demonstration machine. We'll fly 2 to 3 passengers in it. But our team will immediately work on the STC to get to the more commercial aircraft, which we expect to be issued then in 2027. We'll be able to start delivering them at that time. And so based on that, we signed an LOI with Aviation, who's in Quebec, and they signed an LOI for 3 of our eBeaver conversions when they're ready. And if you want to see the aircraft, come and see us at booth 324. And just because we want everybody to know this, our intention is to continue to design and certify retrofit fully electric engines on any aircraft that anybody is interested in. So we're starting with the Harbour Air fleets. We've got the single otters, caravans. Twin otters will likely not be able to go fully electric. We might have to hybrid them, or we'll even test out hydrogen. We want to create a sustainable aviation hub in Vancouver where we can do this, where we have the knowledge and the skill to be able to convert any aircraft anybody is interested in. As I think we say, we want to decarbonize the general aviation, one aircraft type at a time. And are there any other questions? How am I on time? They're lithium ion. So we have protections in place. We put in sort of layers of protection, right? So the first is the battery modules we're flying right now have containments. So these modules have been tested to a full cascading failure of all the cells inside, and it's contained all the heat, all the pressure, all the fire and gas, and sent it out of a venting tube that's in the top. And that's where it became our responsibility. We've got a stainless steel venting system that comes off that and vents it overboard the aircraft. So that's the first layer, 2 layers. What we also do though is thermal runaway due to heat doesn't typically happen until you're above 100 degrees Celsius. So we have a return to base warning at 60 degrees Celsius. If the system gets up to 60 degrees Celsius, the pilot returns to base immediately. That gives them a significant amount of time to get back to base before you get up anywhere near a thermal runaway event due to heat. We also only dispatch the aircraft with the batteries up to a certain ambient temperature. Right now we have an ambient temperature limit. We should probably adjust that to be more about it's the dispatch temperature of the batteries that matter. Out of all the testing we've done recently, we have found that the ambient temperature really only influences the starting temperature of the battery pack. It doesn't have any influence over the rate of rise of temperature in the batteries. So what's influencing that is how much power we're pushing. So I think we determined recently if the pilot's pushing takeoff power, the batteries will rise at about 2 degrees Celsius per minute. If he's in, not our endurance, but our range cruise settings, it rises at about 0.5 degrees Celsius per minute. And at endurance settings, it's flat, right? So part of that is making sure your pilot understands how he's influencing the temperature in the batteries by how he is operating the aircraft. So he's given all that information before flights. We dispatch it at a lower temperature so that even if he flew it at, full takeoff power for a length of time, it would still take him, 15 minutes to get to up to the 60 degrees and have to return to base. Yes, right. Okay, so for this event, because we were really excited to be invited to Oshkosh, we brought a static display. That's what's showing at booth 324. That's intended to show people what our certification aircraft will look like. So if you wanted to fly in one of these aircraft when they're ready in 2027, or if you wanted to buy one yourself, this is what it would look like. So it's got the pilot seat, co-pilot seat, and the bench seat in it. It has a bulkhead behind that. So if you're familiar with the Beaver, there's a sling seat behind the bench seat. We've taken the sling seat out and we've bulkheaded that off because that's where probably a large stack of the batteries is going to go, is where the sling seat was. So that has a magniX 650 engine on it. And then batteries will be forward of the firewall, in the belly, in the fuel bay, and then behind that bulkhead. So you can see what the aircraft will look like when we get it to certification. If you go to the EAA Seaplane base, you'll be able to see our current flying aircraft. So that's our experimental one. It has the Magni 500 engine in it, which is their old version. It's got EP Systems Epic One batteries, lithium-ion batteries in it, and they're all sitting basically in the cabin. That one has a pilot seat in it. It doesn't have the co-pilot seat, but since we were able to do away with auto, there's room now for us to put a co-pilot seat in there. And it's one of our plans when we get back home to Vancouver. We're going to be petitioning Transport Canada to allow us to carry a flight test engineer on boards. Those different aircraft. Yes, we're already seeing some of that. In 2019, they were honestly terrified to sign this flight permit, right? They had no knowledge of how this would work. We also aren't an OEM, so they don't know if our processes were good or we're just some cowboy outfit that's, making stuff up. Since we've performed 89 flights to date, it's definitely become a lot easier with the regulator, with Transport Canada. They trust that our systems are there, that we're doing our due diligence. And so when we, for example, we just changed out the batteries this past year. We finished that in May. We applied to Transport Canada for a new flight permit because we had this new configuration of the aircraft. He turned it around in 3 days. He read through the basic information to make sure that we had our risk mitigations in place, that we had our flight test regimen in place. And he's like, no, we trust what you guys are doing. You're good to go. Here's your 120-day flight permit. And the next step will be negotiating with him to say, okay, we want to remove some of our restrictions, right? We probably still can't remove some of the environmental restrictions, but we'll be able to remove things like our speed limitation. We have a flight envelope limitation right now as well. We're not allowed to go to the edges of the envelope, but we've hired a delegated flight test pilot. And so they're definitely much more lenient and okay, yeah, you need to explore that in the baseline and versus that one to inform your certification. You're using a test pilot, you're using processes that we've become to trust, and therefore, yes, we will give you these accommodations, these changes to the flight permit. They're much more willing to do that now that we've got, 4 years and 89 flights completed. We're getting there. They're becoming more familiar with it. So yeah, I think having the Pipistrel come to Canada, we've got a couple that Transport Canada have actually sponsored to bring in so they can learn a bit more about electric aircraft. Because again, the light sport aircraft category is not approved in Canada. So that's something that they've been trying to figure out, both the light sport aircraft as well as the electrification. So I think in Ottawa, they've got 1 or 2 Pipistrels. So some of the Transport Canada people are actually going up for flights and trying to learn more about it. Really, it's just familiarization is a huge part of this. The technology, if you're operating within the limitations that the people are defining, the technology is quite safe, but they're afraid of the unknown. So once they know it, it'll be much easier. Yes, in a sea can. We actually we bought 2 sea cans. We shipped the static display in one sea can and the flying machine in the other sea can. Yeah, so our poor team here arrived last Sunday. And they spent 4 days assembling both aircraft. So the static display didn't matter that much. We're not rigging anything. It doesn't need to be dualed and all that kind of stuff because it's not flying. But they had 2 days to actually get the flying machine in full flying assembled condition. So they worked almost round the clock, 2 of our people and 2 of magniX's people. But the aircraft are all together now. It was a long week. It was a very long week. Yeah, it's one of the rings we're pushing. So we know that Polestar has 350 watt-hour per kilogram cells in their cars. So it's made us ask the question and go back to our battery suppliers and say, okay, you've got your 220 watt-hour per kilogram cells. Do you have a line on these 300? Because obviously if Polestar can get access to 350 watt-hour per kilogram cells, so could you guys, right? And I do know the battery suppliers are chasing that. But yes, the electric vehicle market is definitely helping push this forward for us to get the technology where we need it to be. But yeah, we're taking advantage of that. And if they have, I didn't know they were an 800 volt system, but that might help with the charging infrastructure issue that we're having. Exactly. We looked around when we were having our charging woes. You do have a couple of charging stations that aren't too far away from the Seaplane base, but they don't go to the voltage that we need. So we couldn't use them. Even if we could crane the aircraft over to those charging locations, they wouldn't get up the voltages we need. So if the car market starts moving to the higher voltage system, it'll help change the charging infrastructure which would support us. We have a lot of conversations, like in particular, I know where we are talking with the marine environments because we're located next to the sea, BC ferries, and we have some tugboats, the high sea. They're all looking at electrification, which means we're going to need a ton of shore power for both the marine and the aviation side. And I think, again, it comes back to that commonality is talking to them and say, okay, what voltage are you guys using, right? What are the systems that you guys are using so that we can ensure we're all able to support the development of the charging infrastructure and make sure that it's useful for all of us. Thank you. Any other questions? There's going to be. And that's one of the reasons why the aircraft sits in the hangar when it's not flying is because none of the components have been tested for salt spray or for longevity, for corrosion. We have right now it's something dumb. It's like a 10-hour inspection on the motor. We have to inspect it every 10 hours to ensure that the coatings are all intact. We don't have very long intervals on any of our inspections right now. We have a post-flight inspection after every single flight. There's a series of inspections we have to do. We have 10-hour inspections and we have 20-hour inspections because they don't have enough data yet on how the engines and the batteries are going to wear, right? So this is definitely something we're trying to gather that data for the suppliers so they can start making some of those determinations. Do they need to change any of their coatings? Do they need to change any of their materials? How are they going to hold up? It's a concern we live with daily, right? So the question has to do with cleanliness and daily bathing of the aircraft, things like that. The theory is we should make no change. They should do exactly to the electric aircraft what they do to the piston aircraft in terms of rinsing at the end of each day to remove salt, etc. All of the components should be designed and certified to withstand any water ingress, right? So because it's going to be operating in that same environment, landing and taking off on the ocean and flying in Vancouver in particular in rain, they're going to have to be able to resist that. So we're changing as little as possible. So the expectation is this should be operated and maintained almost exactly as the original, except that when it comes to actually maintaining the components, the line replaceable units will have a much longer interval eventually. Any other questions? Fantastic. Well, thank you for coming, everybody. I appreciate it.